Welcome back, 7th grade. So we're in your Eureka workbooks, Module 1, Lesson 2 today, and we're going to continue our discussion on ratios by talking about proportional relationships. Now, proportionality, maybe you've heard this word, maybe you haven't. Proportionality is a constant ratio relationship between multiple quantities. So an example from the last lesson would be like, let's say, gallons of gas and the dollar amount. And let's just say like every gallon costs $2, okay, just for simplicity's sake. So a constant ratio would be, well, 2 gallons of gas is going to cost me $4. So these ratios are actually equal because all we did was multiply by 2 to go down here. So these are equivalent ratios. All right, so Eureka gives us an example problem. Allow me to read. All right, so a new self-serve frozen yogurt store opened this summer that sells its frozen yogurt at a price based upon total weight of the yogurt. Okay, maybe you have or have not experienced a store like this, but essentially a frozen yogurt shop, you can put whatever kind of toppings you want. You can get as much yogurt as you want, but then they just kind of weigh it, and then that is what they base their price off of. So each member of Isabel's family weighs his dish, and this is what they found. Determine if the cost is proportional to the weight. Okay, so right down here, this is Isabel's family situation down here. Okay, so we're going to determine whether the cost is proportional to the weight. Is there a constant ratio between cost and weight? So we're going to take each one of these situations. So Isabel has 5 people in her family. Let's give them some names. I don't know. Maybe Isabel got this one. This is the one with the most ice cream. I'm going to call this one Mom, maybe. And maybe Dad is on a diet, so he didn't get as much. And that's our brother. They don't need names. Great. All right. Let's determine if these relationships are proportional. So this box here represents one cost and weight, and the rest of these boxes all represent the cost and weight per cone, right? So Isabel's cone weighed 12.5 ounces, and her cost in dollars was $5, right? So 12 ounces, $5. So that is our first ratio, and we're going to come right down here, and I'm going to write 12.5 over 5. All right. Now, the question is that equal to the ratio of Mom's ounces per cost? So again, we're going to keep the ratio with the weight on top, weight in ounces on top, and the dollar amount at the bottom. Okay, so it's not readily apparent if these are equal right here. 4 doesn't go into 5 real easy. 12.5 doesn't go into 10 real easy. Maybe you have some guesses right here. What's your hypothesis at this point? Do you think just based on the information we have right here, do you think that these are proportional? Okay, those were some pretty interesting responses. Now, I heard someone mention from the last lesson, and I appreciate that you remember your vocabulary from the last lesson. Maybe we could determine the unit rate of the cost per ounce for each. And how could we do this? Well, we would divide the total weight. For example, Isabel's cup had 12.5 ounces over the total cost, which is $5. This will get us a unit rate of ounces per dollar. So remember what we learned about long division. Long division is very important, and we need to know how to do it. So we'll divide 12.5 by 5, and that gives us a unit rate. And remember, what we're doing here actually, just so that there's no confusion, we're actually dividing both parts of the ratio by 5. So we're going to divide 12.5 by 5, and that's going to get us 2.5 over, when we divide 5 by 5, 5 divided by 5 is 1. So for every $1, again, this represented dollars up here, and this represented ounces. For every dollar spent, we got 2.5 ounces, at least in Isabel's cup, right? So now let's go to Mom's cup. Let's see if Mom's cup is proportional. So Mom's cup weighed 10 ounces and cost $4. So 10 ounces over $4. We're going to get our unit price the same way. We're going to divide the total ounces, 10, by the amount in dollars, $4. And again, we see that this time it cost us 2.5. It cost us, we got 2.5 ounces per dollar, right? For every $1 spent, it costs us 2.5 ounces. So yes, at least these two are proportional. But can we safely say that the rest of this is going to be proportional? What about 5 ounces for $2? Well, let's just try it. Let's write this out. Maybe we can see 5 over 2. Let's just do our long division. We've learned how to do long division. 2.5. So again, yeah, we know that those are proportional. What if we look at the last one? Brother got 8 ounces for $3.20. So 8 ounces divided by $3.20. 2.5 ounces per dollar, right? So 2.5 ounces per dollar, and that's equal. They're all equal. They're all an equivalent ratio to one another. So the question, is the price proportional to the weight? The answer is yes. All right, I just wanted to clear some of that off the screen. If you want to go back and look at some of that work, you can rewind the video. So again, the question is asked, is the cost proportional to the weight? Down here, they want us to write in right here. The cost is proportional to the weight. And we determined that the unit rate was 2.5 ounces per dollar. All right, now, before we go in and before we move on, I want to pose a question to you. So let's say, I don't know, big cousin William comes around and he took some time to make his dish. He made his dish real big, and he gets up to the counter and he pays for his stuff, and he comes to sit down and he says that he had to pay $10 for his frozen yogurt. Well, if we know that we get 2.5 ounces per dollar, how many ounces of frozen yogurt did Cousin William get? Take some time, try to figure it out. Great, those were some very creative solutions. Some of you may have noticed that Cousin William spent twice as much as Isabel did on her cone. So you could just extrapolate from that if he had spent twice as much, then he got twice as much frozen yogurt, which would dictate that he got 25 ounces of frozen yogurt. Now, the way we could have used our unit rate to do this was simply multiply 10 times 2.5 to get to 25 ounces. Okay, so Cousin Billy was a big boy, but Cousin Quentin, he's an even bigger boy. He comes back to the table and his cup is overflowing, and he says that he's got 40 ounces of yogurt in his cup. The question is, could you determine how much he spent on that yogurt, given just the unit rate right? So in the last example, we knew the cost in dollars, so we were able to multiply the unit rate to get the amount of yogurt that he had. In this case, he's telling us how much yogurt he has. Can we use the unit rate to determine the cost that he paid? Give us some time to figure it out. That's awesome, Mark. That's real initiative. I appreciate y'all's effort on that. Some of y'all got it right. Now, the way we can think about this, since we can't multiply 40 times 2.5 to get our answer down here, right? That wouldn't make sense. This number is always the amount of ounces is always bigger than the dollars. So if we're going to stay proportional, that's not going to work. But instead of multiplying, we can divide 2.5 40 by 2.5 to get our cost down here. Well, let's see if that'll work with some of these other ones. Let's try maybe 10 and 4. So let's divide 10 by 2.4, 2.5, I should say, our unit rate. We'll divide the weight by our unit rate. Let's try that out. 10 divided by 2.5. You know how to do long division. It's very important. Fantastic. So yes, that worked out there. Will it work out right here? Let's try from 5 to 2. Is that going to work? So let's divide 5 divided by 2.5. Yes, in fact, it does. So we should be able to divide 40 by 2.5. And that would mean big old cousin Quentin spent, dang, he spent $16 on that cup of yogurt. I don't know if they actually do that. I don't know if they'll actually let you get that much in a cup. Maybe, I'm not sure. So what we've done here is we found two separate formulas, right? If we know the total weight, of the ice cream, of the yogurt, we know the total weight of the yogurt, we can divide it by 2.5 to get the cost. So the way we could write that is our weight in ounces divided by 2.5 equals our cost in dollars. And obviously this is some shorthand right here. OZ, that is short for ounce. The ounce of yogurt. Little dollar sign represents total cost. And this is our unit rate, right? Unit rate. So in this example, we had Quentin's 40 ounces. We divided it by 2.5 to get the total cost. In the last example with big old cousin Billy, he had told us the amount he paid, which was $10, and we discovered that we could multiply the cost, however much it costs. For example, $16. We can multiply that times 2.5 to get the total weight in ounces. So both of these formulas are derived from our unit rate. All right, so given this formula right here, does it make sense that if I don't buy any ice cream, any frozen yogurt, that I wouldn't spend any dollars? Well, yeah, it does. I mean, this formula makes sense, and that makes sense in real life, right? But if I put in 0 over here, then it's going to be $0 over here, right? And that would make this statement true. All right. Why don't you go ahead and move down your page, and we're going to go to example 2. All right. So in the back of a recipe book, there's a diagram that provides easy conversions to use while cooking. Maybe some of you have some experience with this. Maybe some of you have done some baking before. These are very common conversions, cups to ounces. So the conversions tell us how one relates to the other, right? And these seem pretty straightforward as we're going. If you have 0 cups, then you have 0 ounce. Makes sense, right? If you have 1 cup, then you have 8 ounces. So just before we keep going, just based on that right there, so 1 cup equals 8 ounces. Which one of these is a larger measurement, the cups or the ounces? It's the cups, because you need more ounces to equal the same number of cups. So if 8 ounces, again, OZ, short for ounces, equals 1 cup, well, that means this one is bigger. That means that a cup is bigger than an ounce, right? All right, so that's just an aside. So 1 cup equals 8 ounces, right? And so as we continue going down, it would make sense that if 1 cup is 8 ounces, then you multiply that times 2 to get here. So you multiply the number of ounces times 2 to get here, right? And that is the case. So the ounces are proportional to the cups, right? And we have a unit rate already set up for us right here. They tell us that 1 cup, so for every 1 cup there's 8 ounces, so that's 8 ounces per cup. That is our rate, our unit rate being 8, right? And we can see that this unit rate will converge both ways, right? So 2 times 8 gets us 16, and then 16 divided by 8 gets us 2. And this will work for all of these, right? So even at 0, 0 times 0 times 8, right? That's our unit rate, gets us 0, yeah? And then 0 divided by anything, 0, right? And we go to 1/2. 1/2 times 8 does get us 4, check, that's great. And we can go back again. 4 divided by 8 gets us 1/2. So these are in fact proportional. All right, so once again, what we can do with this information now that we know that 8 ounces, there are 8 ounces per cup, we can create a formula that relates ounces to cups and cups to ounces. So first, if we want to convert from cups to ounces, well, we know that there's 8 ounces per cup, so we would multiply 8 times the cups, the number of cups, right? Which let's change that to a variable, right? So let's make number of cups equals, we'll just call it C, right? So 8 times C times the number of cups equals, let's just call O for ounces, just to make it a little bit simple. OZ, whatever. 8 times the number of cups gets us the number of ounces, right? What if we want to go from ounces to cups? Well, how did we do it up here? How did we go from ounces to cups right here? Well, we divided, right? We divided 16 times 2. We divided 16 by 8 to get to 2. So we would divide OZ, number of ounces, by the unit rate 8, and that gets us our number of cups. Okay, moving on to exercise 3. We have a chart here that measures the number of calories burned to the amount of time jumping rope right here. So that's what's going on in this graph. The time you spend jumping rope right here on this line, and the amount of calories burned on this line right here. Now, for some of you, and I know for me, it kind of helps me to do this vertically. So what I'm going to do is I'm going to make a little chart. It's the same chart, only it's going to be in a vertical way. So obviously, if you do 0 minutes, and this is time in minutes. So if you do 0 minutes of jumping rope, then you don't burn any calories, right? But if you do 1 minute, then you burn 11 calories. I assume that's calories with the big K. I'm not sure, but 2 minutes gets you 22. So before we even keep going, just based on what we can see right here, do y'all think that this is proportional? proportional? Those are some interesting responses. Let's keep going and let's find out, right? How can we exactly tell? So I'm going to just finish off my little vertical chart right here. How can we tell? What can we do to prove that this is or is not proportional, right? So let's find a unit rate. So a unit rate here, well, we've already got a 1 right here. For every 1 minute spent, we do 11, we burn 11 calories, right? We burn 11 calories. So our unit rate is 11. Yeah. So if we go down, let's just go between 1 to 2. What did we do to go from 1 to 2? Well, we multiplied that times 2, right? We did twice as many minutes of jump rope, right? So if you think about it, we should burn twice as many calories, right? Is that the case? Well, from 1 to 2, we multiply by 2. From 11 to 22, we do multiply by 2, right? And then what if we, at the same note, if we spend 3 minutes now, right? So we go from 1 to 3 minutes, that means we did 3 times as much exercise. We spent 3 times as much time jumping rope. So we should burn 3 times as many calories. And if we believe the chart here, this is suggesting so far everything is proportional. So from 1 to 4 minutes, we spent 4 times as many minutes, so we should have burned 4 times as many calories, which we did. 4 times 11 is 44. So is the number of calories burned proportional to time? A full answer for this would be, and I'm going to give you just a second. All right, so right here is what a full response to that would look like. The number of calories burned is proportional to time spent exercising. So you are writing or have written a response something like this, right? And how do you know? Well, we proved it out over here. So if we did some work right here, that would be an acceptable portion of your answer, right? We know that for every minute we burn 11 calories. And that remains true throughout, right? All right, so from our table, we know that for every minute we spend, we burn 11 calories. So the question is, if Jose jumped for 6.5 minutes, 6.5 minutes, how many calories would you expect him to burn? So I'm going to give you a minute, try to figure that one out. Those are some really creative solutions. I like that. Yeah, very, very interesting thought process there. So what we have here, since we know our unit rate is 11 calories per minute, we can write a formula, right? Just like we did in our other examples. So 11 calories for every minute. Let's write minutes equals M. So 11 times the number of minutes equals your C, big C, calories burned. And we use variables to shorthand, so we don't have to write that out when we write our formula, right? So 11 calories for every minute. So 11 times the number of minutes equals the number of calories we burn. So what we can do now, since we know the amount of time that Jose spent jumping, we can replace that in our formula with the minutes. So 6.5 replaces M. M represents the number of minutes. Jose jumped for 6.5 minutes. And we can solve for the number of calories burned. So 11 times 6.5 great. 71.5 calories. Correct? Yes. Fantastic. Is this proportional? If we divide this by 11, will we get back 6.5? Yes. So again, when responding to constructive response questions, Remember to check your rubric. This right here is an example of an all-star response. If Jose jumps for 6.5 minutes, he expects to burn 71.5 calories. Remember to restate the question. Since that was the question, we restated it in our answer. That would be a beautiful response. Okay, so in your workbook, there's one more example problem, but I'm going to make a second video for this one, okay? Um, so if you are at home and you want to look at this one, I'm going to put that in the second video, and I'm also going to talk about a slightly different way of looking at the first example. Since Eureka describes this one a little bit differently, we talked about a lot of different aspects of proportionality and ratios. So from here, what I want you to do is go ahead and move forward to exit ticket and your problem set. Lesson summary right here. Measures of one type of quantity are proportional to measures of a second type of quantity if there is a similar number that they label as K, so that every measure X, that's any one measure quantity of a quantity of the first type, and the corresponding measure of Y of the quantity of the second type. So that's just two different quantities, right? X and Y. Is given by Kx, which is K times X, that is Y equals Kx. So if you're reading this, there's a lot to unpack here. This is just this is called the constant of proportionality, right? It's that unit rate that we used throughout this lesson to go back and forth between ounces and cost or ounces and cups. So the way they describe it is some number, some relationship, some value Y is equal to K, which is your constant or your unit rate, times X, which is the other value, right? And we're going to be dealing with Cartesian planes where X and Y represent points on a graph, and they also represent where X is the independent and Y is the dependent variable. Independent. Oh, geez. So you may have heard these terms, independent and dependent variable, before in science class. In math, typically X is associated with your independent, Y is your dependent variable. Dependent variable. Okay, so a proportional relationship is a correspondence between two types of quantities such that the measures of quantities of the first type are proportional to the measures of the quantity of the second. I'm in love with this lesson summary right here. Essentially, what that's saying right there is that a proportional relationship, it corresponds to different quantities, right? Like ounces and cups, and that the ratio between those things is proportional, just like we talked about. Note that proportional relationships and ratio relationships describe the same set of word pairs in two different ways. The ratio relationships are used in context of working with equivalent ratios, while proportional relationships are used in the context of rates. All of that is true. In the example given below, the distance is proportional to time, since measure of distance, y, can be calculated by multiplying each corresponding time, t, with the same value, 10. Right, so we multiply 0 times 10, we get 0, 1 times 10, we get 2, 2 times 10, we get 20, 3 times 10, we get 30. So those are proportional. Fantastic. All right. Okay, so you're going to move on to the problem set now, which includes that. That can't be all. You probably have much more. Remember to check your rubric. for constructive response questions. Yes, it's a ratio of 3 to 5. Crayon apple juice. So here you want to make sure that you recognize which one came first in the ratio, right? Crayon apple juice. Then they want you to create a table for some proportional values. You can handle that and explain. Remember, check your rubric for how to respond to constructive response questions. I'll see y'all in the next one.